Most of you have heard about the Flat Earth Society, but do we also have a Flat Wing Society? Coming up. Hello aviators, how are you doing? My name is Magnar, I'm an airline captain and instructor. A few weeks ago I posted a video explaining how Bernoulli's principle, or equation, very often is incorrectly used to explain how a wing produces lift. There's a link to that video below here. Bernoulli's principle is as following. When you increase the velocity of a fluid, the static pressure will decrease and the dynamic pressure will increase, and vice versa. And the sum of the static pressure and the dynamic pressure is constant. This follows the principle of conservation of energy. Static pressure is the pressure when the fluid is not moving. Dynamic pressure is the kinetic energy in a fluid when it's in motion. And if you follow me to the end of this video, I will reveal the truth about flat wings. But first, let's recap the essence of my previous video. Many aviation books and manuals are telling us that two air molecules, or particles, when separated in front of a wing, will meet at the same place behind the wing. And since the upper part of the wing is more curved than the underside, the particle must travel a longer distance. Therefore, it must move at a higher velocity. According to Bernoulli's equation, the increased velocity causes the air pressure to decrease. This is called the equal transit time hypothesis. And while it's correct that the static air pressure will drop when the velocity increases, it's impossible for the air particles over the wing to know the position of the particles under the wing. In a wind tunnel, we can see that the air flowing over the wing reached the end of the wing much earlier than the air flowing under the wing. This is what I addressed in my previous video. I also explained that it is the pressure difference above and below the wing that creates lift. And this resulted in many reactions. Many viewers have rightfully commented that the angle of attack is important for lift, and that lift is created when a wing pushes the air down in accordance with Newton's third law of motion. For every action, there is an equal and opposite reaction. I totally agree. Newton's third law of motion is the easiest way to explain lift. I want to stress out that there is no contradiction between Bernoulli and Newton here. It's not Bernoulli lift or Newton lift. It's Bernoulli and Newton. Both explain the same lift. Bernoulli explains lift through conservation of energy. Newton explains lift through conservation of momentum. In fact, Bernoulli's equation can be calculated from Newton's second law of motion. Professionals are using the Kutta-Joukowski theorem to calculate the lift of a two-dimensional airfoil, the Lanchester-Prandtl theory to predict lift distribution of a three-dimensional wing, and the Navier-Stokes equations for conservation of mass, momentum, and energy. And here is a fun fact. The Navier-Stokes equations are developed from the Euler equations. Leonhard Euler was a student of Daniel Bernoulli's father, Johann. Before we continue, let's look at Newton's three laws of motion. The first law. An object at rest remains at rest, and an object in motion remains in motion at constant speed in a straight line unless acted on by an unbalanced force. Think about an air particle in a streamline. Newton's second law. The acceleration of an object depends on the mass of the object and the amount of force applied. For example, if the static air pressure ahead of a particle is less than the static pressure behind, the particle will accelerate towards the area with the lower pressure, and vice versa. The arrival of a wing will force the air particles to change direction. There will be one airflow over the wing and one airflow below the wing. The two flows are separated at the stagnation point. When the wing meets the air with a low angle of attack, the stagnation point is at the front of the leading edge. When the angle of attack is high, the stagnation point is further behind and below the leading edge. Now, the air flowing around the leading edge and over the top of the wing follows a curved path, right? According to Newton's second law, when the air particle changes direction, It's because of an acceleration. Do you agree? Good. Therefore, there must be a force acting on the particle, and this is the centripetal force. And it causes the particle to accelerate and follow a curved path. Therefore, there must be a pressure gradient across the streamline, where the static air pressure is decreasing towards the center of the curvature. Think about the tornado. And when the static air pressure is reduced, the velocity of the airstream must, in accordance with Bernoulli's equation, be higher. Since the airflow on the upper surface of the wing has a low pressure, it is pushed towards the wing's upper surface by the atmospheric pressure from above. It's not the Coanda effect that keeps the airflow stuck to the wing. I will explain the Coanda effect later on. When the airstream leaves the aft part of the wing, it will continue in the same direction, creating a downwash. And that brings us to Newton's third law. For every action, there is an equal and opposite reaction. And it allows us to explain lift in less than 10 seconds. All you have to say is, a wing creates lift because it's deflecting air downwards. And in accordance with Newton's third law of motion, this creates an equal and opposite force, pushing the wing up. It's that simple. It's a little more complicated to explain why the wing deflects the air downwards. Instead of using Newton's second law, we can explain the acceleration of the airflow around the leading edge by observing the distance between the streamlines. Over the leading edge, there's a Venturi effect, compressing the airstreams. This causes an acceleration, which, in accordance with Bernoulli, causes the static pressure to decrease. Under the wing, the streamlines are further away, which means the airstream slows down. That means the static pressure increases. Bernoulli again. This figure shows the pressure distribution above and below a wing at different angle of attack. As the angle of attack increases, the upper part of the wing contributes more and more to the lift. Maximum lift is achieved at around 15 degrees angle of attack. At higher angle of attack, the airflow over the wing separates, and there is a sudden loss of lift. This is stall. Still, the underside of the wing produces some lift, but it's not sufficient to maintain level flight. And we are getting closer to the flat wing society. And talking about pressure distribution, this figure shows that the static pressure is at the highest at the stagnation point, and that the lowest pressure is over the leading edge of the wing. When you see the rapid change of air pressure around the leading edge, it's easy to understand why the shape of the leading edge is so important. The downwash happens because air is heavy and therefore has a momentum. At sea level, the air pressure is slightly more than 10 tons per square meter. When the air is set in motion, we are talking about serious forces. Just see what a hurricane can do, or a tornado. Lesser known is that there is an upwash ahead of the wing. This is caused by the area with a high air pressure under the wing. Sadly, many illustrations in aviation literature are plain wrong. This is wrong, and this, and this, and this. This is pretty close. Finally, this is correct. Does the airstream follow the curvature of the wing because of the Coanda effect? Yes and no. Yes, because the Coanda effect can be used to increase lift. No, because when we're talking about lift, we are talking about the pressure difference above and below the wing. The Coanda effect works only on one side. So what is the Coanda effect then? Per definition, the Coanda effect is the tendency of a fluid jet to stay attached to a convex surface. In other words, we are not talking about an air flowing around the wing, but a jet that emerges from an orifice. Here are some examples. You can blow air over the surface of a paper. When you hold the paper like this, the paper is curved and will lift up. But when the paper is hanging straight down, the paper will not move much when you blow along one of the sides. The reason is that the static air pressure in your lungs is the same as the atmospheric static pressure. Therefore, the pressure is the same on both sides of the paper, and this cannot explain Bernoulli. Still, it's very tempting to use this demonstration to explain lift, right? This balloon is hanging in the air because the fan is blowing air upwards. The balloon sticks to the airstream. This prevents the balloon from falling down, and gravity prevents the balloon from being blown away. Only when the airflow is obstructed, the balloon will fall down. On the Lockheed F-104 Starfighter is air from the engine compressor directed over the flaps to increase lift, hence reducing the speed at takeoff and landing. Other aircraft using blown flaps are MiG-21 and Blackburn Buccaneer. Propellers blowing air over a wing also utilizes the ground effect to enhance lift. This is the Shimaiwa US-1A from Japan. In addition to having 4 propellers blowing air over the wing, the aircraft has a 5th engine installed in the wing box. This engine blows compressed air over the flaps and flight control surfaces, allowing the airplane to take off and land at short distances. Here is a comment from a viewer. Supersonic airplanes have symmetrical profile wings, so no Bernoulli effect. Also, some aerobatic airplanes have symmetrical profile wings, so again no Bernoulli effect. Okay, let me comment on this. When a wing with a symmetrical profile moves through the air with zero angle of attack, the streamlines above and under the wing are identical, and there is zero lift. But since the streamlines are compressed over and under the wing, the pressure will decrease and the velocity will increase in accordance with Bernoulli's equation. So, how can an airplane with a symmetrical wing profile create lift then? By flying with a positive angle of attack. This causes the stagnation point to move down and under the leading edge, and the airstream over the wing will accelerate more than the air under the wing, just like a wing with an asymmetric profile. All you need is low and a higher angle of attack. And when you fly upside down with a symmetrical profile, you do the same, you increase the angle of attack. Airplanes with asymmetrical wing profiles can also fly upside down, you just need a higher angle of attack. And of course, the aircraft must be designed to fly with a negative G for a prolonged time. And now, what about supersonic airplanes? Supersonic airplanes have thin wings with a sharp leading edge. The wing profile doesn't have to be symmetrical, however. Such wings are perfect for supersonic flight because they create very low drag, but they are not good for slow flight. The F-104 Starfighter is an extreme example. The wings are very small and the leading edge is sharp as a knife. Not razor sharp, but sharper than a butter knife for sure. In order to fly slow enough to take off and land, the wings are equipped with leading edge flaps, called maneuvering flaps, and trailing edge flaps. This increases the curvature over the wing and therefore increases lift. On this picture, the aircraft is flying with the maneuvering flaps extended. On modern fighter aircraft like the F-16, the operation of the maneuvering flaps is automatic. When flying with a low angle of attack, the flaps is retracted. When the angle of attack increases, the flaps extends. Early aviation pioneers were inspired by the birds and copied the shape of the wings. The Wright brothers took it a step further and designed the first wind tunnel. It was important for them to develop an efficient wing because the first engine produced only 12 horsepower. This is a replica of Morane-Saulnier Type G. The wing profile is typical for that era. Without a curved leading edge, the wing would have been almost flat. What makes the wing efficient, at least for its time, is the curved shape of the leading edge. This allows for the air to accelerate and create lift. The sail of a sailboat works in the same way. When the wind fills the sail, it has a curvature, a camber. That means the airflow is following a curved path. And according to Newton's second law, we have an acceleration, which reduces the static air pressure over the curvature, Bernoulli. And on the other side, the static air pressure along the sail is increased. And the pressure difference is lift. As you can see, a very thin wing or a sail can produce lift. The magic happens because of the curvature. Here is another comment. The airfoil shape simply smooths the airflow over the top of the wing. While this does create a comparatively low pressure over the top, it's the higher pressure on the bottom of the wing that pushes the wing up. Yes, the underside of the wing produces lift, but the overside is more important. You cannot isolate one part of the wing from the other. It's the pressure difference between the top and bottom of the wing that creates lift. And since the air is flowing faster over the wing than below, the force is stronger, contributing to most of the downwash. No pilot will take off when the upper surface of the wing is contaminated with snow or ice. It must be removed first. And I have another argument. If the underside of the wing is so important for lift, why do many military aircraft have lots of stuff hanging under the wings, but not over them? Yes, it's more easy to hang drop tanks and ordnance under the wings, but the real reason it's placed there is aerodynamic lift. According to Leslie G. Fries, the chief designer at Bristol Aircraft Company during the Second World War, even a kitchen table will fly if you give it a big enough engine. The fastest kitchen table he designed was the Beaufighter attack aircraft. And the comment section reflects similar ideas about flat wings. You can tilt a flatboard out of your car window and it will violently be pushed upward. Does not require an intricate theory on why this happens. Yes, the flatboard is pushed upward. But is that how a wing works? Yes, but only when it's stalled. An airfoil can be defined as a body which, when set in a suitable angle to a given airflow, produces much more lift and drag. A flat wing doesn't do that. This is a simulation of a flat wing. The streamline just above the stagnation point has to negotiate the sharp corner of the leading edge, which causes it to separate from the surface. This creates a separation bubble behind the leading edge. Not only does the bubble reduce the lift of the airfoil, but as the angle of attack increases, the separation bubble spreads downstream and an early stall occurs. We have to conclude that a flat wing is a terrible airfoil. Some people are arguing that a model airplane with a flat wing will fly. Sure, but only because model airplanes are small, overpowered if they have engine, and they're made of very light materials like balsa and foam. A wing like this is nothing more than a kitchen table. If you scale up a flat wing and install it on a real airplane, it will not be able to fly, I promise you. But a flat plate do have a purpose. Air brakes and spoilers are used to create drag and remove lift from the wing after landing. And a flat plate is perfect for this. But when you need lift, you make sure the air is flowing around the airfoil, creating lift with minimum resistance. In the beginning of the video, I mentioned Navier-Stokes equations for conservation of mass, momentum and energy. The equations are used to model the airflow around the wing. And as I said, Bernoulli explains lift through the conservation of energy, and Newton explains lift through the conservation of momentum. The conclusion is there is no competition between Newton and Bernoulli. We need them both. And when used correctly, they explain the same lift. Therefore, next time somebody tells you about the equal transit time, you know not to answer, right? Okay, that's all for this time. Thank you for watching, have a wonderful day, and happy landing.